Okay, here in example 3, we're going to be finding minimum area. So we want to minimize area. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What dimensions of the page, what should the dimensions of the page be so that the least amount of paper is used? Well, let's start looking through that text and figure out what's important here. A rectangular page, 24 square inches of print. So, a rectangle, we have our length and our width. The area is length times width. So one of our equations is going to be x times y equals 24. X times y equals 24. Instead of using L and W, X and Y are our length and width. And we multiply them together to get the square inches in the area, and we want that to be 24 square inches. And then we have margins. So let's start working on a picture here. So here's our page. Let's call across the top here Y and X up and down the side. And around that we're going to have some margins. So the margins at the top and the bottom are going to be 1.5 inches. So here at the top, we're going to have 1.5 inches. And also at the bottom, 1.5 inches. The margins on the left and right are to be 1 inch. So here on the left and right, left 1 inch. And on the right, 1 inch. And let's find the length and width of the entire page then with the margins. So here we have this length is Y, and then we have 1 inch on either side. 1 inch and 1 inch are 2 inches, so this entire side is Y plus 2. Up and down the length, we have this length of the print is X, and then we have 1.5 inches on the top and the bottom. Well, 1.5 inches times 2 is 3 inches. So this side is X plus 3. So remember, this X times Y is 24 is the area of the print. These lengths and widths, X plus 3 and Y plus 2, X plus 3 times Y plus 2, are the area of the page. So the top is the print, the bottom one is the page. And let's go back and reread here the last sentence. What should the dimensions of the page be so that the least amount of paper is used? We want to minimize least amount of paper. We want to minimize the size of the page, not anything to do with the size of the print inside. So we have our primary equation right here. That's our primary. And remember, we want to take this primary equation and get everything in terms of one variable. So we're going to take this secondary equation, our print one, X times Y equals 24. We're going to solve that for X, or solve it for Y, and then plug that into the primary equation. So if I take X times Y equals 24, and I solve for Y, I'll divide both sides by X. Y equals 24 divided by X. I'm going to plug this value, 24 divided by X, in right here in the primary equation. So I'm just going to replace that Y with a 24 over X. So my primary equation is going to become A equals the quantity X plus 3 times Y plus 2, or now that's 24 divided by X, plus 2. So here's my new primary equation, and it's in one variable. And what we're going to do is just clean that up a little bit. We'll FOIL it out and collect our like terms. Just here we have a binomial, and we're going to FOIL it out. And in the essence of time, I'll just give us the FOILed out and completely collected, all our like terms collected. If you do it correctly, you're going to get 30 plus 2x plus 72 over x. And a better way to write this, because our next step is going to be to differentiate, 72 over x is 72x to the negative 1. So now there's our primary equation all ready to go. All in one variable, simplified, and all our like terms collected. So again, just like we did in the previous sections of this chapter, we want to look for mins or maxes. We want to find critical numbers by setting our first derivative equal to 0. So let's derive with respect to x. dA dx equals, the derivative of 30 is nothing. The derivative of 2x is 2. And then when we derive this last term, we're going to have negative 1 times 72. So it's going to be minus 72 x to the negative 2 power. Minus 72 x to the negative 2. And let's get rid of that negative exponent and drop it to the denominator. 72 over x squared. So we took our first derivative to find the critical numbers. We set that equal to 0. So let's see, first step, I would add this quantity to both sides. So we're going to have 2 equals 72 over x squared. And then to get rid of the denominator x squared, I'd multiply both sides by x squared. 2x squared equals 72. And if we divide by 2, this will divide out and we'll have 36. X squared equals 36. And when we take the square root of x squared, we'll get 2 roots, plus or minus 6. When we think about the feasible domain here, we can't have a negative value. You know, that would be saying that this side of the print here, x, would be negative length, and there is no such thing. So we can throw the negative root in the garbage. So we have our one and only critical number, positive 6. Well, we found our critical number, 6. I'll come up here and write it, x equals 6. We have to make sure, we have to figure out that is a min or a max. And in a previous example, we did the first derivative test. We talked about it. Let's try the second derivative test here. Ooh, and I erased my first derivative. So let's get rid of a little of this. Here's our first derivative. If I were to find the second derivative, d double prime a dx double prime, the 2 will derive off. This would be negative 72x to the negative 2. Negative 72x to the negative 2. When we take that derivative, we're going to have a positive 144x to the negative 3, or that over x to the third. So we have our second derivative. If we plug our critical number of 6 in, we're going to have a positive numerator, 144. A denominator, 6 to the third power, is also positive. Positive second derivative means our function is concave up around that critical number of x. If it is concave up, that means our critical number is at the bottom of that valley. Therefore, it is a relative min, and that's what we were looking for. So now we're sure that x equals 6 is the minimum value to minimize the area of that page. So the only thing left to do is actually find the dimensions of the page. If we come back over to here, this was x plus 3. The side of this page was x plus 3. Well, now we know that x is 6. So here's our printed page. And we know that the length of this piece of paper is going to be 6 plus 3, or 9. And we also knew that we had x times y equals 24. That was our secondary equation. X times y equals 24. Well, if x is 6, we can write 6y equals 24. Divide by 6, we get y is 4. So if we plug that in right here, the width of the page was y plus 2, or 4 plus 2 is 6. So that to minimize the size of the paper that we need to get the printing on it, we want to get pieces of paper that are 9 by 6 inches. That'll minimize the paper that we're using and minimize the cost of production. Okay, here in example 4, we're going to find minimum length. 2 posts, one 12-foot high and the other 28-foot high, stand 30 feet apart. They are to be stayed by 2 wires attached to a single stake. running from the ground to the top of each post. Where should the stake be placed to use the least amount of wire? So here's our stake, and we could place it really close to the shorter pole or really close to the larger pole or anywhere in between. And as we do that, the length of the wires connecting the top of the poles to the ground are going to vary in length. We want to minimize that distance. You know, if this was an industry problem and we had to do this to a bunch of different towers with wires on them, we would want to minimize the length of this wire. The less wire we use, the less our overall cost will be. So let's work on our picture here a little bit. It says we have two poles, one is 12 foot high, the other is 28 foot high. So of course the shorter one's going to be 12, the taller one is 28, and they are 30 feet apart. So this total distance is 30 feet. And they're attached to two wires running to a stake. So we need a primary equation, and that is the one that we are going to minimize. Primary equation. So we want to minimize the lengths of these wires. So, you know, this one will have one length and then we'll have another length here, so we got to give those two different variables. Let's call this wire Y and the longer wire here Z. So our primary equation is going to be, we want to minimize that total length, or we'll use capital W for wire, and that's going to equal Y plus Z. You know, the first Y chunk plus the second Z chunk, that's what we want to minimize. And we are going to need at least one secondary equation. In this one it looks like we're going to need two secondary equations. You know, we need other equations tying these variables together. The piece of the puzzle we haven't used yet is the base is a total of 30 feet, and this stake again is mobile. So as this distance decreases, the other distance will increase and vice versa. So that's always in a state of flux. So if we just take this smaller chunk here on this triangle and call this X, and we know the entire distance between the bases of the poles is 30 feet, we've used up X units here. Our remainder would be 30 minus X. And now if we look at the picture, we can see we have a little Pythagorean theorem going on. We have two right triangles. So here in our primary equation we have a y variable and a z variable. Well, let's solve that first triangle, the triangle on the left, for y. Y equals. If we work with the Pythagorean theorem a little bit there, we're going to have y equals, that's the hypotenuse of this right triangle, so that's going to be the square root of the legs squared and summed, or x squared plus 12 squared, or 144. So there's a primary equation that gives us another way to express y. And let's do the same thing for z. Z equals, we would have the square root of, our two legs on this triangle are 30 minus x quantity squared plus 28 squared. And what we can do is expand that binomial and square the 28 and collect our like terms, get everything together, and what we're left with under that radical then is x squared minus 60x plus 1684. So we have our primary equation, the one we want to minimize, W equals the lengths of the two wires, and we have expressions for the lengths of those two chunks of that wire. So we can now write our primary equation. I'll switch to black here. W equals, and we had y plus z. Now we'll substitute in for y, x squared plus 144 plus our value for z, x squared minus 60x plus 1684. And this would also be a good time to consider our feasible domain. What values can x take on? Remember, x, you know, are inputs to this function. What is the feasible domain for x? X has to be a number, of course, between 0. We can't, you know, at most it would be length nothing. And at very most, across the base of this triangle, or these two triangles, we know the max value would be a 30. So that's our feasible domain. When we derive and find our critical numbers, we'll check any interior critical numbers, and we'll also check these endpoints just to be safe. So there's our feasible domain, and we have our equation. Our primary equation is now written in a single variable, everything in terms of x. So here we get to derive. And this, it might be good practice to even try to do this on your calculator. This will become a very complicated derivative, and cleaning everything up and setting it equal to 0 is going to be pretty complicated. It is useful to learn to use the buttons on that TI-89 also. Well, if we derive dw dx, this is, in other ways, this quantity to the half power. So our derivative is going to be 1/2 that quantity to the negative 1/2 power, which would drop it to the denominator. So we're going to have our x squared plus 144 in the denominator. And the chain rule says we have to tack on a 2x, our inner function's derivative, plus our second square root here. We had that same thing to the 1/2 power. We're going to have 1 up top, 1/2, and then we're going to have that radical unchanged in the denominator. And now our inner function's derivative is 2x minus 60. 2x minus 60. And if we look here, we can see a couple things. We can simplify each of these fractions a little bit. These 2's will divide out nice and easy here. And this 2 will divide out with what's going on in the parentheses here. That'll wipe out the 2 in front of the x, and that will divide this 60 down to a 30. That's a minus 30 then. And let me rewrite this so it looks a little prettier. We're going to have x over our radical x squared plus 144, plus our numerator now here in this second term is just x minus 30 over our larger radical x squared minus 60x plus 1684. And what do we do with our derivative after we take it? We set it equal to 0. So it doesn't look like we can factor this left side. I'm just going to subtract this second term from both sides. That will wind up on the other side of the equals, and it will become negative. And a real easy way to make this negative is just to distribute a negative throughout the numerator. So that x and that 30 are going to switch places. We're going to have a 30 minus x. Again, that's the same thing as distributing a negative across there. So what we're going to have here is x over the smaller radical, x squared plus 144. And that's now going to equal, again, I switch my numerator to distribute that negative, and that's over that larger radical denominator. Well, now we have here a fraction equal to a fraction. We can cross multiply. So if we cross multiply there, we're going to have x times our larger radical, x squared minus 60x plus 1684. And that's equal to the quantity 30 minus x times the square root of x squared plus 144. Now we have nasty radicals on both sides of the equal sign. So let's square both sides. As we square both sides, we're going to take care of that radical. We're going to square this binomial. Squaring this term will take care of the radical again, and we'll have an x squared term there. So after the squaring, we're going to have x squared, and then a parenthesis now contains what used to be under our radical. And we're going to have 30 minus x quantity squared times the quantity x squared plus 144. Now if we distribute the x squared, if we FOIL out this 30 minus x quantity squared and distribute it throughout this x squared plus 144, we're going to get some big polynomials on each side, and then we'll get everything on one side to condense it. For the sake of time, I'll get this all FOILed out and simplified down. We're going to wind up with a 640x squared plus 8,640x minus 129,600, and that's now equal to 0. We can factor out a 320. And we factor that out, we'll have x minus 9 left. and a 2x plus 45 equals 0, and that's fully factored down. So I factored out the 320 and then factored the remaining polynomial. I can divide out the 320, that's now gone. And if I set each term equal to 0, I'm going to get an x equals 9. Or here I'd move the 45 over and get a negative 45 and divide by 2. So that would be x equals negative 22.5. And you know, a negative x value in this problem does not make sense. You remember, x is the length of this smaller side of the right triangle. If we put a negative in there, you know, that doesn't make sense for a length in this problem. So we can throw this out. So we have our one and only critical number at x equals 9. And again, we want to check the endpoints of this problem just to be safe. We have had, you know, in our min and max over an interval, you can have a min or a max occur right at the interval. So, oops. If we go back to the original equation and we evaluate w of 0, w of our critical number 9, and w of our right endpoint 30. If we plug w of 0 in, we get approximately 53.04 feet of wire. If we go to the other endpoint, w of 30, we get approximately 60.31 feet of wire. And if we check our critical number on the interior, we get a nice even 50, and that is our minimum. And you can graph that to verify. You know, if you got your TI-89 out, graph to verify. And you can check that out graphically. Okay, in each of the first 4 examples, the extreme value occurred at a critical number. Although this happens often, remember, an extreme value can also occur at an endpoint, and we're going to see that in this example. And if we think back earlier, you know, when we were doing just our mins and maxes, we had our xy axis and we had our some interval from a to b. And you know, the function would start here and then maybe go up and down and then back up. And when we were looking for mins and maxes, you know, we would identify the critical numbers. We might have a min or a max here, a min or a max here. And yeah, this here was a local max. But if we kept going and we checked out the extreme endpoint of the function, this was our global max across that interval. So it is a good idea, always check those endpoints. We can have mins and maxes occur there. So in this example 5, it says 4 feet of wire is to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? So our primary equation, that's the first thing we always want to find here. Our primary equation is what we want to max or min, and here it's maximum total area. So if we think, you know, total area is going to equal, we're using that wire to shape 2 figures, a square and a circle. So the total area is going to be the area of the square plus the area of the circle. So our primary equation is simply going to be area equals, you know, the area of this square. We're given each side length x, so x times x is x squared for the circle, plus the area, or area of the square, plus for the circle, pi r squared. So there's our primary equation. Secondary equation. We have the constraint of 4 feet of wire. We have 4 feet of wire to enclose the area in. So we're talking about the perimeter of the circle, or the perimeter of the square, or the circumference of the circle. So secondary equation. And this is going to deal again with perimeter or circumference. And the perimeter of the square is going to be 4 times x plus the circumference of a circle is 2 pi r. And we are given the constraint of 4 feet. So this is going to equal 4. And again, what this secondary equation is used for, we're going to solve this for a variable to plug it back into the primary equation. If we look at the primary equation, there's only 2 variables. There's an x and there's an r. So if we take this equation and solve for r, and we can plug it back in here for this r and square it, we'll have our primary equation in a single variable. So let's take that secondary equation and solve it for r. I'll rewrite it here. For 4x plus 2 pi r equals 4. And again, we're going to solve for r. So first thing, subtract out of 4x. 2 pi r equals 4 minus 4x. And we want to get the r variable alone, so we're going to divide by 2 pi. So we're going to have r equals, and let's factor a 4 out of that top. 4 times 1 minus 1x over 2 pi. And here the 4 and the 2 will cancel down. That'll reduce to a 2, and that'll reduce to a 1. So r equals 2 times the quantity 1 minus x over pi. This is the value of r that we're going to substitute into our primary equation right here. So area equals, we have our x squared plus pi, and we had r squared here, but now we're substituting in the r that we found, which was 2 times the quantity 1 minus x over pi. And this is a quantity squared. And when we have that quantity squared, it's like we're going to distribute that squared throughout. It'll go to the 2, it'll go to the quantity, it'll go to the pi in the denominator. So area equals x squared plus pi times, well, we're going to have 2 squared, or 4, 1 minus x quantity squared over pi squared. And now we can eliminate this pi with one of these. So we can scribble out that exponent. That's just now pi to the first power. And to make this a little better to work with, let's FOIL this out. We're going to FOIL that out and distribute the 4. So when we do that, we're going to have a 4 minus 8x plus 4x squared all over pi. And let's see, we got a fraction here with a pi denominator. We'd like to have a common denominator. So here, to get the common denominator under the x squared, I'd multiply by a pi. And if I do it to the denominator, I got to do it to the numerator also. So we'll put a pi up top there too. And yeah, we'll just work with that for now. So we're going to have everything now over the common denominator pi. And we're going to have x squared plus 4 minus 8x plus 4x squared. And I forgot my pi that went with that x squared. You know, this was pi times x squared. So that is a pi x squared, and we do have a 4x squared. And let me copy that so I can take it to the next page. So that denominator I don't like so much. If I sort of bracket this off, I can drag that pi in the denominator out front, and I can make that a 1 over pi fraction. And now I just got inside my parentheses. Will be a little easier to work with. And here I have a 4x squared and a pi x squared. So those are sort of common terms with the x squared leading after it. So I can rewrite that as a 4 plus pi x squared. And then I'll have a minus 8x plus 4. So it's not the prettiest function I've ever seen, but we do have our primary equation, area equals. Now it's all in a single variable x, and it's cleaned up enough that it shouldn't be too bad to take the derivative. So we're going to do dA dx. This 1 over pi pi is an irrational number, but it's just a number anyway, and that is the constant multiple rule. So when we take this derivative, that 1 over pi will remain. Let's see what happens in here now. 4 plus pi, again, that's just a number. You know, if this was a 3x squared and we derived it, would bring the 2 down and multiply, and it'd be 6x squared to the, or 6x to the first power. So when we derive this, 4 plus pi is just a constant. We're going to bring that 2 down front. We're going to have 2 times the quantity, 4 plus pi, and then our x now has dropped down to the first power. And then when we derive 8x, it's just minus 8, and then our 4 derives right off, and it's no longer there. So we've taken our derivative, and now we're going to set that equal to 0 to locate any critical numbers. So we set this equal to 0, and the first thing I would do would be to divide by this 1 over pi. I can divide it out of the left side. 0 divided by 1 over pi is still 0, so we don't have to change anything there. And now we're just going to solve this for x and see what our critical numbers are. Let's add this 8 to both sides to get that out of there. We're going to have 2 times the quantity 4 plus pi times x equals 8. We can divide by 2, and that'll turn this into a 4. And then we'll divide both sides by the quantity in the parentheses to isolate x. So we're going to have x equals 4 divided by the quantity 4 plus pi. And we can estimate that or just round it off as a decimal. 2 places should be enough. If we punch that in the calculator, you're going to get about 0.56. So we've found our derivative, set it equal to 0, found the critical number. We're going to check that critical number and the endpoints in the original function. So a of 0, a of our interior critical number, 0.56, and a of 1. So we were trying to maximize area, so we want to find which of these is the largest. When we plug in a of 1 in the original function, we get an output of 1. When we plug in our critical number, 0.56, we get approximately 0.56. If we do a of 0 in the original function, we get a value of 1.273. That is by far the largest. That maximizes area. But a of 0 gives us max area. What does that mean? Remember what x stood for. If we go back to the original setup, x was the length of one side of our square. And what this is saying is, let x equal 0. Do not use any of your 4 feet of wire to make a square at all. If you want to maximize your area, use all 4 feet to create your circle. That will maximize your area. So again, we don't want to use any of that wire on the square. We want to use everything on the circle. And that's a good example where an endpoint can be our min or max value. If you don't set up a feasible domain and don't check those endpoints, it'd be real easy to miss a correct answer like that. Now let's take a look at the primary equations we developed in the first 5 examples. As applications go, these 5 examples are fairly simple, and yet the resulting primary equations can be complicated. When we did our volume problem, we had 27x minus a quarter x to the third. The wire problem that we did 2 examples ago, we used a little Pythagorean theorem and got this radical plus another radical. For the parabola problem, we had the distance formula that we had to work with. This last one with our area of the wire used to make a square and a circle. You must expect that real-life applications often involve equations that are at least as complicated as these 5. Remember that one of the main goals of this course is to learn how to use calculus to analyze equations that initially seem formidable. And remember, when you're doing the homework or anything and you run into some very complicated equations, use that TI-89 to find the derivative and set that derivative equal to 0. You'll be allowed to use it on the AP test, so at least for the harder homework problems, use that calculator as much as you need.